Uh, is it visible, my screen? Can you see my screen?
Yes, yes, visible, sir.
Okay, 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 great.
Visible.
Okay, so then let's start. Good afternoon, everyone. My name is Mrinmoy Bhattacharjee. I've currently very recently joined as a postdoctoral researcher at LEAP Lab in Indian Institute of Science, Bangalore. Previously, I was at IDIAP Research Institute in Switzerland. So this session is part of the summer school on recent trends in speech processing and its applications. Today, I will be talking about the problem of movie genre classification using audio features. So this will be the outline of my talk today. I will first start by describing what the problem is and why we need to solve the problem. Then I'll discuss what was the motivation to start this problem and how we designed the hypothesis. After that, I'll discuss how the problem was tackled by splitting it into different subtasks, and then how we tackle the main task. I'll finally give the conclusions that we derived from this work, and finally, I'll give some broad directions in which the work can be extended in the future. I hope you'll find this work interesting and we can have opportunities to collaborate in the future. So, movie genre classification. What is it? Why do we need to do it? And how do we do it? So, first, the definition of movie genre. Genre is basically a stylistic or a thematic category based on the similarities in the narrative elements. That is, the the story of the movie or how a particular plot is being presented in a movie. What is the underlying characteristic of that? Which follows a particular aesthetic approach or a particular set of emotional responses that are expected from the viewer. That is what a genre is. Types of genre that we popularly see in movie labels are action, animation, biography, comedy, crime, etc. Now, this is not an exhaustive list which I have mentioned here. There are lot of different fine-grained genre labels that people use for labeling movies, but this is a it's a very popular set of genres which more or less every movie would have one out of these particular genre labels. Now, there are different data sets that are available which we use for this task. So different data sets would have different set of genre labels. So the problem would that becomes difficult to compare across different works. But in an average sense, we can say that if we can detect these set of genre labels from the movies, we are more or less doing a good job in this task. Now, why do you have to do this movie genre classification automatically? Until now, the genre labeling of movies is done manually. So people in you might have looked at websites like IMDb or which give the are basically doing crowdsourcing from their users, and the users go to the website, select a movie, and then mark the label which they think a particular movie should have. Now, every movie doesn't need not necessarily have only one label. It can have multiple labels. For example, it can be a romantic comedy, or it can be a action comedy, or it can be a thriller and mystery. There might be combination of many genre labels, but basically the labeling that has been done till now are done manually. But over the years, the viewership of movies has increased many folds. That we all know and understand. So, as the number of movies being produced increases, manually labeling these movies would become a very tedious job, and also it would not be very correct, or in many times it would be very so subjective that it might not help in our goals. So, in this scenario, what we would need is an automatic tool which can process the movie as a set of signals, video signals, audio signals, and other related metadata. And based on the signals that it receives, it can predict what kind of genre this movie might have. If that automatic tool works well, then first thing, the subjectiveness of manual labeling would be removed, and also the scale at which movies are being produced, we can tackle that also easily with a tool. How do we use such a automatic genre classification tool? The few example applications that could happen, that could be used in this case, are underage censorship. So there are movies which are labeled as adult or children. Now, this labeling is again done by a certification board, which is again a subjective manual job. If we can do it automatically, then we can in make these tools inbuilt into the search engines, and based on who is using the system, based on the person's age, the system can itself filter out those content which the person should not be viewing. Other could applications could be choice based query retrieval. So I suppose I go to a website and I want to view a comedy movie. So I'll just maybe ask it to give me the list of all comedy movies. Now, right now, what happens is it checks the metadata of the movies, and then only those movies which have the label of comedy, it returns those. But if we have an automatic tool which has already parsed the movies and found out what are the genre of the movies stored in the database, it can give me the list of all the movies in the database. And also the movie makers can use such a tool for target publicity of their movies. Now, in the graph you see here, this shows the scale of movies that are being produced that I mentioned in the first point. The first graph is for the Hollywood movies revenue growth. Over the years, it has been rapidly increasing, and it means that more number of people are viewing movies, and hence more number of movies are being produced. So this is a continuous trend. A new phenomenon is the OTT platforms like Netflix, which are increasingly becoming more popular. Now, the bottom graph shows how the revenue of Netflix has grown over the years. And here also we see even a more sharper rise in the revenue, which indirectly indicates that the number of viewership, the number of viewers who are accessing these online content are increasing, as well as the number of movies that are being produced over the years, or the content in form of web series and others are increasing gradually. Now let us discuss how this movie genre classification is performed. Most previous approaches have used a multimodal approach, which means that they have used all the different modalities associated with the movies. The different modalities would be the visual modality, that is the video, the audio modality, that is the under the audio subtitle, sorry, the audio that is associated with the video, and also other metadata like subtitles, that is the text transcripts of the speech segments, or the other meta informations that are associated with the movie, or some image information like posters that the movies are used, the posters that are used for publicizing the movies. So different works in previous works have used different combination of those, but mostly they have, people in past have focused on the visual or the image modality. Audio has been used only as a, how do you say it, auxiliary modality, without giving much thought about how audio can be used better. Recently, earlier people used to process the whole movies, but that was a cumbersome job because the movies are very long in length, and it would require a lot of processing if we need to process many movies at a time. So recently, people have opted to process only the trailers of the movies, which are shorter, of 1 to 3 minutes long, and the trailers are designed in such a way that they carry the underlying theme of the movie. So just by looking at the trailer, you can understand whether the movie is of a comedy genre or of a horror genre or other any other genre. So the recent works in this domain have mostly focused on processing the short trailers of movies to reduce the computational load, and also to uh, process more number of movies at a time. How the movie trailers help us in doing this? Because the movie trailers, as I have mentioned already, have the general theme of the movie in it. They are also specifically designed so that they can evoke the genre specific emotional responses in the viewers. And as I mentioned, they require less time, computational overheads. And another important point about this is movies are only obtained after they're officially released. But trailers are released much before the movies. So if we process the trailers, we'll already have the genre label even before the movie is released. And as soon as the movie gets released, it will be available for searching using genre based search methods. Now let's come to the motivation of this work. As I have already mentioned, people have mostly focused on the visual modality. Audio is used, but it is used very as just as a supplementary data. Not much thought has been given to process audio in a more suitable way. Uh, but people who work on audio in different other tasks of audio, they understand the fact that audio in itself is a very rich information source, and it can give us a very nuanced understanding of different things, in this particular case about the movies or what the genre of the movie is. Hence, the my motivation to do this work was the very importance of audio, and I wanted to show in a way that if we process the audio alone, we can still do very good genre classification, even though multimodal approaches would still be better. But with a better audio processing pipeline, the overall system would be much better. Now, when I listen to the audio of movie trailers, I can understand that it is mostly composed of speech and music signals. So there would be some dialogues, and then there would be many kinds of music, which kind of highlight the underlying emotional or the scene that is being portrayed in that particular segment of the trailer. So if it is a, for example, if it is a high speed chase, you'll have a very specific kind of music playing. Or if it is a romantic scene, there will be a very slow kind of music which is being played, which will never be present when there is, for example, a horror scene being displayed. So there are differences in the kinds of signals that are used, and that is what this work hypothesizes, that if we explore these audio categories and try to map them to different genres, we will be able to better classify the genres of the music of the movies. Now, to further convince you that the audio content is important, it is observed that the movie style is determined by the audio content, not the visual content. And the directors or the sound engineers of movies, they do very specific sound editing, so that a very particular set of uh, effects or emotions are evoked in the audience. And it is also observed that the audio aspects are very strongly related to the affective scenes, where if a particular kind of audio is used, people feel sad. If a particular kind of audio is used, people feel angry. And these very nuanced kind of editing is done in movies, so that people feel can not only view the movie, but they can feel the various scenes in the movies and kind of live through the plot of the movie. Also, movie audio, as I mentioned, is a very rich signal. The visual aspect merely shows you the various scenes and objects that are present in the movie, but the actual story that is being portrayed by the movie is contained in the speech content. So the dialogues that people have, and or the voiceovers that are there sometimes, that is what tells you what the actual story is. Apart from mime movies, which did the same thing without any dialogues or speech, all these new movies that are made today are heavily dependent on the speech content to carry forward the storyline. And similarly, music is used to evoke different sentimental responses in the viewers. Apart from that, there are different other sounds like environmental sounds and other acoustics which help to enhance a particular scene. For example, if there is a train scene, you'll have the sound of a train running in the background. If there is a person riding a horse, you'll have the sound of the hoofs hitting the ground. These are there to further make the scenes realistic to the viewers. So as we have seen that audio is very important for the movies that are made now. So, and I have uh, presented to you that speech and music are the major constituents of the audio of movies. So, what is the distribution of these signals in the movie audio? So here in these two graphs, you can see the distribution of speech and music across different genres of a particular data set. So this should not be seen as the general trend of all movies, but uh, the data set that I have in which previous work has been done, which is relatively a large data set that consists of 5,000 movie audio movie trailers. I have only extracted the audio from that. So this gives you an idea that the speech and music content vary across different genres. For example, in the center bar, you'll see the bars for the comedy genre. You see that for the top one is for speech. Sorry, the top one is for music, and the bottom one is for speech. So the comedy genre has less amount of music in it, whereas the it has comparatively most amount of speech across all genres. Similarly, if you see the horror genre, for example, the last second last bar from in the right, here music has lot of the music is present more frequently than speech, which kind of seems to be intuitive because music people don't say, sorry, in horror genres people don't say much, but there is music in the background which helps in like making viewers feel horror or fear. So this is how we observe the differences in the different genres, the composition of the audio of different genres, and this uh, convinced us that we should explore this direction and see if this helps in the genre classification. So how did we approach the task? So we approached it in different incremental steps. The first subtask that we did was to try to classify speech from music, because we know that there will be speech and music present in the movie audio. If we are able to classify speech and music properly, then it will help us in finding out all the speech and music content in the movie audio, trailer audio, and then we can further process it to do the genre classification. So first subtask was basically to we tried to propose features and methods to properly classify speech from music. And the second task that we did was in speech music classification literature, people had mostly explored the magnitude information, but we tried to explore the phase information as well, because that is also an important complementary information compared to the magnitude information, and we tried to see if that also helps in this speech music classification. Once we were able to do a very efficient speech music classification, We then move to a more difficult problem, which is the detection of speech overlapped with music. In movie trailers, you will frequently find that there is dialogue being said, where along with that there is a background score playing. So it is very frequent to observe these overlapping speech and music segments. So if we just try to classify speech from music, we'll miss out those segments, or we'll wrongly identify these mixed segments as speech or music. So we needed an approach to not only detect clean speech and clean music, but we also needed to detect segments where both speech and music are present, maybe in different kinds of mixture or different uh, ratios of mixtures, but still we need to detect those segments. And finally, when we were able to solve all these tasks, we use those methods that we developed to perform the main task of this work, that is a movie genre classification. So let us look at the first subtask, where we propose magnitude features for speech music classification. Now, again, to do this work, there are speech music classification data sets which are obtained from different sources but not movies. But since our target domain was movies, we had to uh, create a speech music data set which where the speech and music signals were obtained from movie audio, so that the methods that we develop can be tested on the in-domain data and validate whether the methods are working well or not. So this data set that we contributed, and it is available publicly for people to use. It has around 8 hours of data, where it has been labeled into 7 different categories, where clean speech and clean music are two of those categories. Clean speech is of around 1 hour 48 minutes, whereas clean music is around 1 hour and 51 minutes. The rest of the data is of different other components like noise, speech with music, or speech with noise, music with noise, etc. This All the validations of the methods in the work that I am going to describe have been done on this data and many other data sets. So the first method of doing speech music classification is using magnitude features. So here in the bottom two graphs, you'll see uh, the spectrum of two particular frames, very randomly selected frames of speech and music. You'll see that the spectrum has a lot of many peaks and troughs. The peaks indicate where there is a lot of energy in the signal, and troughs are the regions where there is very minimum energy of the signal. Now, if we view this spectrum in a two-dimensional representation, which we call a spectrogram, the peaks are the uh, information that we observe as striation patterns in the two-dimensional representation. I'll show the spectrograms in future slides, where I'll highlight that part. So what I'm trying to point out here is the peaks are the most important aspect of the spectrum, and in this work we try to extract the important peaks that indicate whether the signal is speech or music. And for this, what we've done is this flowchart that you see is basically trying to extract the prominent peaks in each of the spectral frames across the signal and store them for further processing. So the approach is very simple. We take the magnitude spectrum. We first identify all the peaks, the ones that you see as rounded points in the spectra in the bottom. We identify those the peaks of the spectra. So for each peak, we'll have the peak location, that is the frequency of that peak, and the amplitude of that peak. So we keep both those informations, and from a given spectra, we don't retain all the peaks, but we have a selection criteria where we retain only the peaks that satisfy the selection criteria, and then all the peaks that pass that criteria, we store their amplitudes and frequency locations. So here are the spectrograms that I was mentioning. This is the two-dimensional representation of the spectra, where the y-axis is the frequency of the signal, and the x-axis represents the time. So here the red regions are the regions that are represented by the peaks I showed in the previous graph. So wherever there is red, or red is the high energy segment and blue is the other end of the spectrum, very lowest energy or no energy. So we are only interested in the high energy segments or the red regions in this representation. These are shown for monophonic music, polyphonic music, single speaker speech, and multi speaker speech. For each of these categories, you'll see that, the the patterns that are represented in this two-dimensional representation, the spectrogram, are slightly different. In the music case, you'll see more or less the patterns are horizontally linear. Here it is much disturbed because it is a polyphonic music. Lot of many musical instruments are playing, so the patterns get disturbed. But yet you can observe that it is more or less horizontally linear. Whereas the speech spectrograms have some wavy patterns in the spectrogram, which are not horizontally linear, but they can be curved, have a wave-like patterns of different structures. It has no pattern to it, but the but the structure seems to be segments of a wave. So the approach that I mentioned previously, that approach helps us extract only these important high energy segments. And once we extract those, we can plot that into the two-dimension plot and see how it looks. So if you see the brown subfigure of each of the each of the figures, you see that only those segments are only those patterns are visible here, which correspond to the high energy patterns in the original spectrogram. So here you see this curvy nature has also been captured. So this shows that the method to extract the important information from the signal has been working, and we are able to discard other information which may not be necessary for our task. Once we have this information, we use this pipeline to compute a feature. So in this pipeline, what is basically being done is each of the peaks here, you see, if you consider one particular peak, it will belong to a particular frequency band. So if we consider all speech data that we have in the training set, in a particular frequency band, you'll have across time, you'll have many peaks that are present. So if we uh, divide the frequency into such bands, and we just uh, for for the first iteration, we just take the peaks that are obtained within only the first frequency band across all data in the training set, then we'll have a one-dimensional sequence of peak locations, which will seem to be a, a, a signal, a one-dimensional signal, or a set of one-dimensional points. What we can do is we can train a Gaussian mixture model on this set of one-dimensional points and find out the distribution of these peaks in that frequency band. So this way we can, for the other frequency bands, we can train a different Gaussian mixture model. So each of these Gaussian mixture models will basically capture the distribution of the peaks in different frequency bands. That way we'll be able to use that information to uh, to detect or to match a signal which we don't know whether it is speech or music to these to the likelihoods given by these Gaussian mixture models. And the higher, if we get a higher likelihood from the speech, the Gaussian mixture model is trained on speech data, then the test signal should be a speech signal. Or if we get a higher likelihood from the GMS from the music data, then the test signal should be a music signal. This is the basic premise. So we split the frequency into different subbands, and for each subband we train a Gaussian mixture model separately for speech data and separately from music data. So suppose if there are 10 such bands, so we'll have 10 Gaussian mixture models from the speech data and another 10 Gaussian mixture models for the music data. Now, once we have these Gaussian mixture models trained, we now go for feature computation, which is stage two, where given an input signal, we first do the peak selection, and then we pass the peaks to these Gaussian mixture models and obtain the posterior probability from these mixture models. The posterior probabilities, if the signal is purely speech signal, the speech gmm should give a higher posterior probability, whereas if it is a music signal, the music posterior should give a higher posterior probabilities. Whatever probabilities we get, we concatenate them into a single vector, and that vector becomes our feature vector. Now, once we have the feature vector, we can simply pass it to a classifier. This is the basic architecture of the DNN classifier used in this work. We are doing a two-class classification into speech and music, and here are the results that we obtained. So we can compare it with four different baseline methods and six different feature combinations. So when we have the peaks, we can also compute some very naive statistical measures like mean, variance, and also we can compute the features that I just mentioned using the whole pipeline of GMMs. So those GMM based features are labeled as CBOW, which is basically short for uh, component bag of words features. Whereas the simple naive features which you can generate is the mean standard deviation. So MSD stands for mean standard deviation. So in the from the table you can see that the mix, and also there is another thing that I have to mention which I previously alluded to. So we always retain the amplitude and the frequency location of the peaks. So the whole process of feature extraction can be done separately for the amplitude information and separately for the location information. So in that sense, we can have two different representations, two different feature vectors. So we try to use both separately and then combine the amplitude and the location information in this case. And we see that the combination of the amplitude and location information with these CBOW features gives us the best performance uh, compared to all the baseline methods that we used. This results are on the movie data that I mentioned previously. Now we also tested it on a different data set which is obtained from TV broadcasts. Since TV broadcasts are also a similar kind of data domain, we tried to evaluate our methods on this data set also to further validate that the method works in these kinds of signals. And here also we observe that although the proposed method doesn't perform as good as the baseline in this data set, but we get very comparable results. Now we have to note here that the baseline method was trained on this data set, on the training set of this data set, and tested on its test set. So the baseline method had already seen this kind of data, but our methods were trained on our movie data set, which had never seen this kind of data. Even then, it was giving comparable performance to this baseline method, and which was quite encouraging. So, to summarize this work, we proposed a novel peak, as the method we call it as spectral peak tracking method. So, we proposed this method to extract a feature in a two-stage pipeline, and we explored two types of features. One is the mean standard deviation feature, the other is the component bag of words features. And this component bag of words features, which in combined which combined both the amplitude and the location information, gave us the best performance. And we have also explored the combination of the proposed feature with uh, more state of the art deep learning end-to-end models and like bottleneck features and other methods. And we observed that even though the method that we propose individually does not perform better than the bottleneck features, but when we combine the bottleneck features with the proposed feature, we get better performance than the bottleneck features alone. So that is interesting aspect of this. And we have explored, we have seen how, tested the method in challenging domains of movie and TV broadcasts, and we have got very encouraging results. Now let me go to the second subtask. If anybody has any question, you can please interrupt or I'll continue.
Excuse me, sir. Can you go
Yeah,
back to the diagram where we are computing that?
this one.
Yes.
Okay.
Okay. So here we are, this GMM classifier is computing our CBOW features. And
Yes.
and the
Yes. Mhm.
and we are computing the LSPT features differently here.
LSPT is basically this pipeline that I showed you. So this here we are extracting the peaks and then storing the amplitude and the location information separately. So the representation of the information would be similar. If you have a two-dimensional, suppose this plot, here I am plotting the amplitude at these frequency locations. But if I only take a matrix where for each frequency band I take the peak, the amplitude of the peak across all the frequency bands and across time, then it will be a matrix of, suppose if there are 10 bands and there is 10 frames in the signal, then 10 cross 10 matrix. So we'll have a 10 cross 10 matrix for both amplitude and for location. So this matrix, here you can see these matrices that I have shown, which may not be visible properly, but these are the matrices obtained from small segments of the audio. Now we take all the values at the, suppose the lowest row in each of the segments across all speech data. That will be a set of values which are one dimensional in nature. So we can simply train a one dimensional GMM over that to get the mean and variance of that distribution. Now, these matrices can either be the amplitude information or the location information. So here this figure is shown only for the location one, so hence it is represented as LSPT. But this can very well be as ASPT and ASPT both side, and we'll get the ASPT CBOW feature.
Got it, sir.
So once we have both these features, we can do the early fusion or late fusion, whatever we need.
And in that, this is all the proposed features. In that way, there are also the classical features like MFCCs are also
Yes,
mentioned.
yes, yes. So here you can see one of the baselines is the MFCC feature.
So this is the features which they have computed on their own data set, and this is the result they have given. And
Uh,
you,
no, no, because in this problem, the issue is there are many data sets which people use. So it is difficult to, because if there had been one particular test set in which people compared the results, then we can simply code their results. But this is not the case. So I had to compute, by keeping all their experimental settings same as they mentioned in the paper, I had to compute the features and obtain the results. So these results I have computed using their setup.
okay, and you have just used this as a baseline features, and
Yes.
then you have executed this. Okay, sir,
Yes.
got it.
Yes. Okay. Any other questions? Okay, then I'll continue. So the next task that I considered was how phase features, the same, the problem was same again, speech music classification, but the previous work mostly used the magnitude information. The magnitude spectrum was used to obtain the features, and all the baselines and all maximum, most of the previous methods have focused on the magnitude information. But we all know that the signal, the speech signal, has a magnitude component and a phase component. Now, people mostly ignore the phase component because of the phase wrapping issue, but there are approaches which can circumvent the wrapping issue and obtain representations which can capture the phase characteristic of the signal. And people have shown those features to work in different approaches like phone classification or other different speech based applications. So with that motivation, I tried to explore three specific features which were proposed previously by other authors to show that how the phase characteristics were captured in these features. The first feature that I used was MFCC computed over the HNGD spectrum. So HNGD stands for Hilbert envelope of the numerator of group delay. The group delay is a uh, uh, concept where it measures the uh, phase characteristics across different subbands in the signal. Now, the authors have shown that rather than using only the group delay, I mean the group delay in totality, they showed that only the numerator of the group delay representation gives a more stable signal, more stable representation. So that they extract the numerator of the group delay and do a Hilbert envelope of that to smooth out the small fluctuations. And once we have this signal, we compute MFCC in the standard approach, how it is computed in the for the speech signal. The MFCC is then computed on the HNGD spectrum, and we get a feature representation which captures the formant structure of the speech. This is how it has been proposed in literature. The next feature that we explored was the modified group delay capsule coefficients. Here also, people have used the group delay representation, but they have used a modification on the group delay computation formula. I'm not going into the computation method formula of the group delay method. You can refer to the original papers because the focus of this talk is more on the speech music classification and the movie genre classification. So basically, the modified group delay formulation is used to get a representation of the group delay or the phase component of the signal, and on that, capstral coefficients are computed, which is called the modified group delay capstral coefficient (MGDCC), and this is shown to represent the frequency derivative of the phase spectrum. And the third feature that I explored was the instantaneous frequency cosine coefficients. And these coefficients, this feature is shown to or has been uh, explained to be representing the time derivative of the analytic phase. So the modified group delay capsule coefficient represents the frequency derivative, whereas the IFCC, that is the third feature, represents the time derivative. So as you would know, derivative represents the rate of change. So one of the feature represents the rate of change across the frequency domain, the other represents the rate of change across the time domain. Now these, here I'm showing the representations of the different features. So the first subfigure, this is for the music signal. The first subfigure is the standard DFT of the signal. The same signal segment has been used to compute all these representations. So as I have mentioned previously, you will again notice that there are horizontal linear striation patterns in this standard DFT. Now, when you compute the HNGD of this HNGD spectrum of this signal, this is how it looks. From this spectrum, we compute the MFCC to obtain the feature. Now, the modified group delay spectrum looks like this, which seems to be quite noisy, and this is shown in the results that we observe that this for this particular task, the modified group delay spectrum doesn't help us much. And which I mentioned earlier was the time or the frequency derivative of the phase, the phase of the signal, and the time derivative of the phase is represented by the instantaneous frequency spectrum, which is represented here. Similarly, for the speech signals, again the standard DFT is shown in this figure, which you can see has this wavy characteristics. The HNGD spectrum is more smoothed representation, so it kind of smooths these harmonics, but you still see the patterns here. The modified group delay is again quite noisy, but it can still show you the rate of change across the frequency. So here there is some pattern present, which is captured by the MGD. And the instantaneous frequency spectrum, which shows the time derivative, uh, kind of shows that at this in different times how the signal is varying. So here there is kind of a the rate of change is seems to be less, and here the rate of change seems to be higher. So these different aspects of the phase information are captured by these features, and we try to see if this helps us in classifying the speech and music signals. So to perform the classification task, we have to first see whether the mm, the signals are or the features are any have any significant information. So statistical significance tests shown here indicate that although the magnitude features are better in the classification of speech and music, but when we combine the magnitude features with the phase features, we because of the complementary nature of the two information, we can expect some improvement. This is the classifier architecture, which is basically a CNN-based classifier, which has fully connected layers as classifier at the end. And it is again by a two-class classification problem. In this table, you see that the performances of different methods are shown. The baseline features here are again the magnitude features that I showed previously, but we are comparing it with the performance of the phase features. If you observe the phase features on their own don't perform as good as the the magnitude features, but when we combine the magnitude the phase features with the magnitude features, we get significant improvement in the performance. uh, this graph shows the pairwise combination of different phase and magnitude features, and here also we see that every pair the performance of the combination is better than taking the magnitude features alone. We also tested this in across data sets and in noisy scenarios by adding artificial noise to the signal. And in all cases, we see that at least some of the combinations of magnitude and phase features do give us slightly better performance than the baseline where only the magnitude features are combined, which is the yellow bar. Compared to that, not all combinations of magnitude and phase features give us improvement, but at least there are some combinations which give us slight improvements. So now this is the performance on the TV broadcast dataset that I mentioned previously. Here, previously, as I had mentioned, that the proposed feature, which the models trained on the proposed feature on a different data set, gave comparable performance, but not better than the baseline in this data set. But in for this particular case, we see that uh, the performance of the phase features alone are not that good. But again, when we combine the phase and magnitude features, we again give comparable performances. So to summarize, we explored three features which are supposed to capture different aspects of the phase spectrum. And when we combine the phase features with the magnitude features, we observed improvement in different scenarios, in clean scenarios, in noisy scenarios, in cross data set scenarios, and in different types of domains like TV broadcast data sets. So this shows that phase information can be a useful aspect of the signal which can be explored further. But overall, the performance gains obtained using phase information is not that significant. So to uh, to build a system quickly, I think the magnitude features would be a better choice. If there are no questions, I would proceed.
Sir,
Yeah.
that P1, P2, P3, they are different feature vector are used, right? I mean, the
Yes.
P1.
Yes.
So you have
Mhm.
mentioned some feature vectors. So
Yes.
different ones are used in there. Okay.
Yes. And we use them individually, and also we use them in combination, pairwise combination, or combining all together, and we see how the performances vary. So overall, one of the phase that is P2 is seen to give better performance among the phase features, and few combinations like all magnitude features and P3 gives us the best performance. But again, the even though there is improvement, uh, the gains are not that significant statistically, at least in this task. So it is a mixed result.
Okay, sir, one question. So
Yeah.
here we are trying to differentiate the speech and music by
Mhm.
by by looking at how much phase shifted they are. I mean, the phase shift is the key attribute which we are
Yes.
which
Yes.
are
Yes.
making by this feature vectors.
Yes. Yes.
Okay, sir. What it's
Yeah. So now I think I don't have much time. So I'll quickly go through this third subtask. So as I mentioned, speech music classification alone would not help us in the movie genre classification because we have music overlap with speech frequently. So to detect these overlap scenarios, we explored the harmonic percussive decomposition, which is basically uh, approach to extract out the harmonic components in the signal as a single representation and another representation that captures the mm, percussive components. What are harmonic components? Those are basically the the striations you see uh, as parallel lines across the frequency range. So if you see the spectrogram, so uh, if I hope these are not very small, if you can notice here, there are very fine parallel lines across the frequency. These are the harmonic components which are how to call it, generated because of the resonances present in the instrument that is producing the sound. So if it is a speech signal, then the vocal tract has its own resonances. So those resonances give us these different patterns in in the frequency domain. uh, if it is a music signal, the different musical instruments that we have their own resonances. So whatever be the signal, it will have these harmonics and resonances present, and it will be viewed in the spectrogram. So the harmonic percussive source separation basically tries to separate these components out. So this is a very clever way of doing this. uh, the representation in the second row basically represents the harmonic component, although it seems to be very noisy, but it tries to basically extract the harmonic components. Now the third row shows the percussive components. The percussive components are basically separated over time. So these are very noisy regions in a particular point in time where there has been, suppose, if, as you know, impulse signal has a uh, uh, this kind of a pattern in the spectrum where it has equal energy across all frequencies. Now, whenever we are speaking, we produce some stop sounds or consonants which have these kind of characteristics. In music, however, these percussive sounds are basically generated when a particular instrument is struck with a with a hand or something. Suppose we are playing a drum or tabla. Every stroke of the instrument generates these kind of impulsive sounds, which are represented in the spectrogram as uh, uh, these noisy, these kind of patterns in the spectrogram. So the percussive decomposition tries to retain these patterns. So if you observe, these patterns are separated in the harmonic and the percussive decompositions. So the first column is for the music signal, the second column is for the speech signal, and third column shows the speech mixed with music at equal ratios. So here, uh, although it's very small to view it, but if you take my word for it, the patterns as we see in the music and speech spectrograms separately get merged together in the speech music spectrogram, and we see both the patterns present there. So the basic idea is that if we decompose the harmonic and percussive components of the signal, the speech plus music or the speech overlaid with music signals will show characteristics of the harmonic characteristics of both speech and music, also the percussive characteristics of speech and music. that will help us distinguish between the signals. Here is a TSNE plot of these decompositions. And so the left one shows the TSNE plot generated without any decomposition from the raw signal. And the right subplot shows the decomposition of the plot obtained after doing the decomposition. So you can see that the decomposition, the harmonic percussive decomposition, helps in improving the separability of the two classes. So this again motivates us to explore this direction. Along with this decomposition, we try to use the multitask learning framework that is popular in the machine learning community, where it is shown that if a task is supported by some auxiliary tasks in the while training the model, then the base task is the performance of the base task gets enhanced because it can learn some more generalized feature representations that will help in the overall classification. So we use three different auxiliary tasks, which are basically, first task is music versus non-music. So anything that is pure music is considered as music, everything else is considered as non-music. Another is speech versus non-speech. Again, anything which is pure speech is considered speech, and everything else is non-speech. And the third is the SMR prediction. Now, SMR is basically what we define it as speech music ratio. So this represents the ratio in which speech and music signals are mixed in the signal. So if it is a pure signal, then obviously the ratio would be speech would be 1 and music would be 0, or vice versa. But if they are mixed in some ratio, then it will have that value. Now, when we use these auxiliary tasks while training the main task, that is the three class classification of speech, music, and speech overlapped with music, then because of these auxiliary tasks, the model doesn't overfit and it can learn more generalized features or embeddings, which can help in the overall performance of the classification. So we try to weigh the different tasks differently. This is a standard practice in multitask learning framework, and we saw that equally weighing the task in this case helped more. Here is a comparison of the methods on the movie dataset that I mentioned previously. What we do is we take four different baseline methods and we use their individual features and classifiers and obtain their results on this dataset. Then we modify these baseline methods by converting their features into the decomposed features of harmonic and percussive, and their classifiers are modified by adding the multitask learning layers at the end. And then we do the classification again, and we observe that for all the methods, although at different scales, but we observe improvements for all the methods. So this indicates that this decomposition and the multitask learning framework taken together helps us in this task. Explore these across different mixing ratios, and we see the same trend. Also, the
Hello, sir.
models are not trained on the TV broadcast data again, harmonic percussive decomposition and multitask learning, even without training on this dataset. So proposed approach.
Sir, you are not audible, sir, and screen is also not visible.
Hello,
Yes, sir.
was I not audible?
No, sir. You are not audible. You have struck from that where you were slowing there. Next, the second Austrian and Swiss slide. And you,
Uh, Sorry. Uh, did I started this? Did you miss this part completely?
sir, your screen is not visible.
I'm sorry. So I was discussing this task. Did you miss this completely?
No, sir. We
Okay.
have listened it. You
Okay.
just uh,
So I
yes,
was here.
yes, you were there, and
Okay.
you
Okay.
just discussing it, and then you got disconnected.
Oh, okay. Okay. Sorry, there was some network issue. So uh, so basically this method was shown to improve, like earlier I mentioned, the proposed methods could not perform better than the baseline method in this TV broadcast data set, but this task was able to give us a slightly better recall value even without training on this data set. So this is an encouraging observation. So I'll quickly summarize that we use the harmonic percussive decomposition to extract features and use the multitask learning framework to train better classifiers. And this whole setup gave us very significantly improved performances in different scenarios. Are there any questions, or I'll proceed?
Hello, sir. I have a question.
Yeah, sure.
Sir, can you go back to that where um, we are actually what we are doing? Harmonically, we are.
Hmm.
Per- now the thing I've forgotten. So actually, we are actually doing what? We are generate. Their harmonics are there in music and speech as well, and the percussive layer are there. So in
Hmm.
speech, this percussive layer are because of this unvoiced sounds, I guess.
Yes, yes,
And the music is you have told that because of that strokes of that guitar or when I press when I struck the tabla. So
yes.
after that, what we are doing, we are extracting what in this percussive harmonic percussive source separation. I mean,
So once we have this decomposed spectrogram, so this is the harmonic spectrogram and this is the percussive spectrogram. So after that, we don't actually compute any feature out of it. We directly pass it to the classifier. The classifier processes each of these representations as it is a CNN based classifier. So it uh, uh, the CNN kernels move over the whole spectrogram and try to learn the patterns in that representation. So we have, so if we learn a classifier on only the harmonic decomposed signal, it will try to learn the differences between the signals from the harmonic perspective. Another classifier which is trained only on the percussive decomposition, it will learn the difference between the signals from the percussive point of view. Now, if you combine both of these, we'll get the distinction between the different signals from, for example, you consider them as two channels. Earlier, if we use only the standard DFT, where both harmonic and percussive information are combined together, the classifier will have to do a lot of work to find uh, the patterns which
tuning.
are different between the signals. But if we do the separation previously and give it to the classifier will find it easier to find the separations, because we know that the harmonics of speech and music and the percussive components are very different. So we'll help the classifier to easily learn the difference between the signals and do a better classification. So that was the basic idea.
Okay, so we are differentiating the percussive nature and the harmonics from that speech and music spectrogram, and then we are passing it to a classifier, and after
Mhm.
that it is distinguishing by learning itself
Mhm.
that which one is speech and which one is music.
Exactly. Exactly.
Okay, sir. Clear, sir. Thank you.
Okay. Okay. So now let me go to the main task, which is the main goal of this work, movie genre classification. Now we have different approaches that I discussed. So each of these approach will be, sorry.
Yes,
I
Vala.
have question. Yeah, that I just wanted to ask question to relate to an African context.
Yeah, yeah.
due to the fact that there's problems related to such research in Africa.
Mm-hmm.
I was taking a scenarios of Hausa movies. There was a language called Hausa. So naturally, they used to blind multiple generics within a single film, which makes, I think, it will make it very difficult to classify them into distinct generics based on solely on audience features. Is there any some technique someone can be able to manipulate to classify such?
Uh, can you please repeat the first part? It broke, so I couldn't understand.
Yeah,
Yes.
what I'm saying is that in the case of the Hausa movies, they use
Mm-hmm.
to blind multiple generics within a single film. In a single
Oh,
film,
okay.
you'll see
Okay.
due to the problems of this dialecent and
Mm-hmm. Yeah, yeah.
problems of accent and all these things, multiple languages, which
Mm-hmm.
makes it very difficult to classify them into a district one based solely on audio feature. Is there any uh, advice or methodology that someone can?
Basically, this problem that I have worked on is a multi-label classification. So every movie has at least two labels. It's very rarely the case that one movie will have only one genre label. So you have to expect that because its movies are long kind of long documents which can have multiple aspects to it. So as I mentioned, it multi-label scenario is the most common case, and we have to tackle that. We have to be prepared for that and have to tackle that. So the data sets that I have used mostly have these multi-labels. Some movies have two labels, some have three labels or four labels. So what we do is, in base normal classification, we predict one class for a given example. In multi-label classification, we don't predict one class, but we predict, uh, so we give a score or a probability for all the classes. So like when we do softmax, we are getting softmax is done only when we have a single label classification. So whichever class has the highest probability will be, the signal will be assigned to that class. But in multi-label classification, each of the outputs are independent of the other. So whatever score we obtain for each of the labels is considered as a score for that label, and that is retained. So in these scenarios, we don't use the standard metrics, that is accuracy or F1 scores directly. Rather, we use some metrics called area under precision recall curves, which when you compute the precision recall curve and compute the area under that curve, that basically gives an indication of how well the model is performing in this multi-label scenario. Does this answer your question?
Yeah, very clear, sir. Very clear.
Okay.
Thank you.
Okay. Okay, sure.
Sir, is it also true for Indian movies as well? No? In India, specifically in South Indian movies, there are no specific genres. I mean, they make the masala movies, which is genre mess up of various elements. There is romance, there is action, there is drama, all are combined together. So this is
Yes.
also applicable for our movies as well.
Yeah, yeah, sure, sure, sure. Obviously, because as you would appreciate, that movies are very complicated signals, and it has been said in the literature that genre is a very high level concept which has no relation or direct mapping with the underlying low level features, be it audio features or visual features, because you cannot say that a particular kind of audio will always be related to a particular genre. This is a very complicated kind of task, and it is very similar to how people do emotion classification. Emotion is also an very subjective kind of an labeling. uh, it differs across cultures. So some cultures express their emotion in a particular way, other cultures express it in a different way. So it's same with movies. The way Indian movies kind of represent a particular emotion, for example, mm, uh, uh, comedy in Indian movie, for example, would be represented in a particular way where there would be a lot of gags, and people would be, how do you say, some funny actions would be there. But in
Slapstick comedy.
Yeah, and in other Hollywood scenario, they use a lot of dry humor, where there would not be a lot of gags, but they'll use the simple dialogues to evoke the laughs from the viewers. So it varies across cultures. So it is very difficult to kind of uh, build a system for movie genre classification which works across all systems. I'll show you some results in the upcoming slides where we did this comparison. But the thing is, uh, the ideas would work across all industries, but then we'll have to fine tune our models on if we want to build a system for the Indian movies, it has to be fine tuned on Indian movies because it has its own complexities. But once we have this model, it will become better than using human annotating these movies, because humans always come with their own biases and subjectiveness. But the system would not be will at least we will try to make it uh, such that it doesn't have any inherent bias. So in that way, a movie can have not only one, but it can have multiple n number of genre labels of different kind of weights. Suppose something is 60% comedy, 20% action, something like that. So that is quite possible, and that should be more helpful for us in the future. Does it answer your question?
Yes, sir. Thank you, sir.
Okay. Okay. So for the main task, we use all the three systems that I discussed previously as parallel tracks, and try to combine these methods together to do the final movie genre classification. So to do this task, we proposed a classifier architecture which is based on attention and has convolution layers in it. I'll discuss the classifier. We have also explored the popular transformer-based classifier that is very popular now. But since we did not have much data with us for training a classifier transformer model, we couldn't get very good results with that. But I plan to collect more data, increase the size of the data set, and then train these transformer models and see if that helps us attain the state of the art performances that are obtained with the visual modality by using only the audio. This is the classifier architecture that I was mentioning. If you see, these are convolution layer blocks, and these are parallel branches. So as many features as we have, we can pass them to each of these branches, and each of the branch will process one feature type and gradually reduce the size of the feature uh, and increase the channel dimension of the convolution layer kernels. And once we reach the final layer, we will pass it to a attention mechanism block where we have two types of attention. We experiment with a time axis attention, which is the standard way of using attention, but also we use a channel axis attention where we try to see if any of the CNN kernel outputs is more useful than the other. So this is done using the attention mechanism. And we also have a parallel branch where we pass the, so once we do the speech music, speech overlay music classification, we'll have the labels of speech music across time for a given movie trailer. So it can be music initially, then speech, then music, then some speech overlay to the music. So that sequence of speech music over the whole movie trailer, we compute that, and we pass that whole sequence as an input to the as a parallel branch. And this is also passed through the attention layers. And once the attention layers give the output, those outputs are combined and passed to these fully connected layers to do the final classification. Now, since I mentioned this is a multi-level classification task, so each of the outputs are considered, whatever output we get, each of the output layers are considered and used for the metric computation. Now, the attention block that I mentioned, this is how the attention is computed. So I'll very briefly describe how this is working. So suppose this is the output of the convolution block. This is passed to a kernel, learnable weight matrix, which transforms the output of the convolution layers into the dimension that we require for the attention mechanism. We add a bias term to it. Then we passed it through the 10H nonlinearity, so that everything comes within the range of -1 to 1. Once we have this, we pass this with basically take a product of this with another trainable weight vector. Then, and the output of this product is passed to the softmax nonlinearity, so that we get the attention scores. So the alpha is basically the attention scores. These attention scores are then multiplied with the original output of the CNN blocks, so that only those, if it is a time axis attention, then only those frames of the audio would be enhanced which seem to have more relation to the underlying genre. If it is a channel axis attention, then those channels will be enhanced which seem to have more relation to the genre that it has been labeled as. And finally, we do a weighted sum of these uh, weighted these attentions weighted features, and this weighted sum is then passed to the classification layers. Here, this is how the transformer encoder-based classifier was designed. Although this did not give us very good results because we lacked enough data, but the idea was very simple. It was similar to the previous classifier. We have separate tracks for the different features, and we only use the encoder part of the transformer model, and we can have multiple stacks of these encoders for each of the features. The output of each of these branches are combined and passed through a time axis attention only here, and then the combined attention output is passed to the classification layers for classification of the genre. For baselines, we use two approaches which have recently been presented, and they show good results. We also use the data set that this paper has proposed, which has around 5,000 movie audio trailers. And also this work is an Indian group which has also released a small data set of Indian movie trailers, but it has only 100 movies in it. So we use this data set to perform the cross data set evaluation. The system basically uses 30 seconds of audio as a single unit, because since this is a very complicated task, we need a lot of context to the performance, and this is done taken similar to the approach followed by the baseline paper. We have tried intermediate and late fusion strategies, where in intermediate we do the combination of features within the classifier at a particular layer, and the output of that combined layer is then passed for classification. Whereas in late fusion, the outputs from the different classifiers obtained are uh, combined after the classification is done, and then we get improved classification performance. And as I mentioned, since this is a multi-label classification, we have to use the popular way of evaluating these models, which is called the uh, area under the precision recall curves. And we show the macro, micro, and sample weighted averages of these values. So first, the results on the movie scope dataset, which is the 5,000 movie trailer dataset, which is one of the largest in this domain. B1 and B2 are the two baseline methods I mentioned, and S1, S2, and S3 are the three systems that I discussed previously. We see that S1, which if you recall, was the method that used the GMMs to calculate the posterior probabilities of speech and music and generate a feature vector. This method gave us the best performance. But when we combine all the methods together, we get the even better performance than using each of these methods individually. And we see that it is better than the baseline methods. Now, to note that the baseline that we considered, the people have also used the other modalities in the data. They have shown performances of individual modalities and also combined the modalities. Here we are quoting their results for only the audio modality. But in combination with other modalities, obviously the performance is much better. But since our focus was only to explore the audio modality, we just compare with the audio modality. And in future, we can see how this method in combination with the other modalities helps. This is the macro, micro, and simple weighted averages. And here also you can see that the proposed approach gives better performance than the best baseline method. And here is the cross dataset performance that I was mentioning. Since Hollywood movies and Bollywood movies have very distinct cultural differences, so obviously the methods would not perform as good as they would if they were trained separately in the in-domain data. But even here, even in the cross dataset scenario, the proposed method combined with the baseline method. So this is the baseline method. The proposed method performs slightly worse than this, but when you combine the proposed method with the baseline method, we get even better performance. So to summarize, we use the GMM based method performed the best among all the systems, and the speech music predictions, that is the sequence of speech and music signals segments in the audio movie trailer, helped in this task. The attention-based CLN classifier that we proposed gave us the best performance, and the results show that the utilization of speech music segmentation information helps in this movie genre classification task. So also the generalization performance was decent. So we can say that the proposal that speech music information from the movie trailer audio can help in genre classification stands validated. To conclude, like we show that handcrafted features based on domain knowledge, that is the features that we used in the first method, helped in this task, and hence it shows that domain knowledge can be important. Although phase information gave us some improvement in combination magnitude features, so it can be explored in future for much better performances. Separation of harmonic and percussive components was a useful step which helped us in this task. And finally, the distribution of speech and music signals in the movie trailers is a very important information that helps us in discriminating the genres of the signals. As future extensions, we can look at different directions like detecting the musical instrument that is present in the music signals or the vocal modes of the speech segments. We can do further refined classification of speech music and speech music mixed with environmental sounds. We can detect and track various sound effects like laughter or fight scene, which may even further help in detecting some particular genres. And then the comparative study of the visual and audio modalities, and to understand for which genres which modality works better. That can be an interesting way of looking forward. There's a few of the references that I've used. Thank you for your attention. If you have any questions, please, I'll be happy to answer.
So,
Yeah, please.
so yeah, the last framework which you have mentioned, that is same for all. So we are doing what? Taking three different approaches and we are passing it to that, and are making that how it is performing, how well they are predicting, right? So in the
Yes.
last, you have the Gaussian-based probabilistic approach, the phase, and which the harmonic recursion-based. The third, the those three are combined and put in that classifier, and it is giving the best performance.
Yes, the final combination is not done at the classifier or the feature level. Rather, it is done on the score level. So we obtain the scores from each of the methods separately, but we combine the scores. So suppose for a particular test example, this method gives it to be a comedy. This gives to be a horror. This also gives us comedy. So in majority, that is selected as comedy. So that is how the score fusion is done, and the score fusion appears to help in improving the performance further.
Okay, so you haven't done the model level or feature level fusion. You have done the score level fusion, and
Yes, yes.
we have separately you have passed it to three different models. Then the scores which are there, then you have fused that together.
Exactly. Yes, yes.
Okay.
The other approaches can also be tried, but then I like it was time constraint was also an issue there, and also uh, to efficiently do that, because the each of the features are in itself of high dimensions. If we combine them in feature fusion, then we'll have much larger feature dimension, and to process that, the whole model size would like explode. So those are the considerations which kind of made me explore the score fusion first, and since it gave good performance, I stopped there. But we can explore, we can design ways to combine them in other methods as well.
And in that convolutional neural network layer, where we are actually decreasing the dimension of a vector, the feature vector here, this is also we are doing it because to reduce the load on the classifier. I mean,
Yes, that is one reason. The other is we are reducing the feature dimension, but we are increasing the at least to some layer. We're increasing the channel number of channel or kernels in the convolution layer. So that way, the dimensional information is getting encoded in the convolution kernels. So different kernels become representative of different aspects of the signal. So of to some extent, the feature size is reducing, but it's not getting reduced to a very small size, because then we'll lose a lot of information. It is rather being used as a transformation of the input feature to a different space, so that the different kernels at the last layer can encode a very specific aspect of the signal, and then we can select between the different kernels to see that which kernel captures the most discriminatory information, which and the kernels which don't capture discriminatory information. The channel axis attention then helps us to suppress the channels which don't capture much information and enhances those which capture better information. That way, it can improve the final classification performance.
so that was very clear. So one final question is, we are collecting this data from the public, we are taking this data from the public domain, but you have mentioned that transformer-based approach to so that we need a big data set. So how we can collect the data? Can we not collect the data from the YouTube because of the copyright issue? So I is the
Even the dataset that I've used, the movie scope dataset that I mentioned, it is also a dataset generated by using the trailers posted on YouTube. Uh, the issue with YouTube videos is that many of these, I mean, people, not all of the trailers listed in that data set are from official channels. Some are from some private channels. So those channels sometimes get, or those videos sometimes get suppressed by YouTube because of copyright infringement and all. So uh, the if we can list, because listing all the movies along with their genre labels is a very difficult task. The authors have done that for these 5,000 movies. Even then, when I tried to download all the movies, I couldn't get all of them because some were removed from YouTube. But I was able to at least get some 4,900 something from the from YouTube. But now, if someone tries to download those, maybe some more would have been removed. So this is, and you cannot share the trailers directly, because that again infringes the copyright issue. So this is one of the challenges in this domain. But if we can somehow list all movies that and their corresponding genre labels, and keep on collecting their trailers over time and store them somewhere, it can become a good resource for future work.
So, for this in genre classification thing, we are completely focusing on the speech, so on the music. So can we also focus on the image and the video, image stuff? Can we relate both to get a better performance
Yes,
in
yes, that's what other works do. Basically, people mostly focus on the image and the visual aspect of the trailers, and then they use audio as additional modality. I have done the opposite thing. I've tried to explore audio in more detail. Now my future goal is to keep this system as it is. I'll try to add other modalities to the system and see how the performance improves. Because as I mentioned, it is a very complicated task. You cannot get the best performance using only one modality. You have to use multiple modalities because, for example, as I mentioned, I showed you a histogram of the distribution of speech and music in different genres. Now, that histogram, if I combine and compute a histogram of how much audio is present in which genre, we will see that different genres have different amounts of audio content, or different what do you call it, different amount of speech and different amount of music present. Some genre may not be at all be well recognized with the audio modality alone. Some genres may be very well detected by the visual modality. So we need to find a balance and decide or determine the genres which are specifically identified better by the visual modality, and those genres which are better identified by audio modality. And when you combine those, definitely will get a better performance. So that is one of my future goals. Let's see what happens.
Thank you very much, sir. So if anyone having any questions, you can feel free to ask, sir.
Oh, that was the question. You already explained it, sir. I was trying to ask if multimodal data integrations by effective synchronizing the combinations of the virtuals and audio features can improve the classification accuracy. And you really explained
Okay.
vividly.
Okay.
Sir, does anyone have any questions? Sir, I want to ask another thing that you have mentioned while in the speech, when we are seeing the harmonics, there is a wavy patterns are there, and in that music part, the patterns are more straight line. Is it because of the window size, or is it because of something else?
No, it is because our vocal track system is said to be a damped system. So when we are speaking, whatever sound unit we produce, it's the sound is produced for a very short amount of time, and then we move on to the next sound unit. So uh, for example, suppose you hit a drum with a stick, the sound that it produces would continue for some duration. You'll keep hearing that sound with gradually attenuating volume, and after some time it will completely stop. But for our system, since our vocal tract is made of soft tissues and all, that ringing or the same sound getting produced for longer period doesn't happen. So each of the sound, when we are, and since we speak in a very complicated set of sound units, every time you're producing a particular word, it is composed of many sound units which span different frequency regions in the spectrum. And so since we're moving from one sound unit to another, and the first sound unit doesn't it gets very decays very soon. So we move in the spectrum, we see that one particular frequency sound is generated. The very next instant, we generate a different frequency sound, which may be above or below it. That way, as we move from one sound unit to another over the whole sentence, we'll see that the spectrogram has the patterns in the spectrogram get uh, move in a wavy pattern from one unit to the other without any horizontal stretching of each of the sound units. But that doesn't happen in music, because although some instruments have that characteristics, but in general this is how the pattern is. In music, if you generate different sounds, each of the sound will ring for some duration, some finite duration, and then it will go off. So the damping characteristics of the human vocal tract is the main differentiating factor in this case.
For that magnitude based approach, I mean magnetic based features. So here we are taking the segment size as a word length or a simple 30-second normal hand window.
That is simple 30-second window. Here, since it it can have speech, music, and other kinds of sounds also. So it doesn't make sense to do any kind of ad or anything like that. So whatever, if we take a random window of 30 seconds, whatever sounds are present in that, we'll try to uh, compute a representation of that whole duration into a embedding, and that embedding will either will try to map that embedding to a particular set of genre labels. If we take very short windows, the fluctuation in the predictions will be so high that it will be difficult to uh, uh, get a very good performance with that. So people generally use longer duration because since it is a very complicated problem to map the raw features to the genre information, a longer context would be helpful to give it the context of the signal and how, how the different characteristics of the signal are varying in that duration, so that a better classification can be done.
Okay. So no segmental feature is used. Only 30 seconds duration of normal features are used so that we can get the information of speech and music as well, and the fluctuation isn't so high that can't understand anything. Oh, sorry, was dropped. Hello, Bala. Are you able to hear anything?
No, it was silent. I can hear anything.
I think Sir's video got stopped.
Yeah, it's possible, and it's almost time. So I think we can give it free time.
Hello, sir. Are you there?
I got disconnected again. Did you hear my answer?
No, sir. Can't hear anything.
Oh, sorry,
So
sorry.
are you able to listen? Are you able to note my question?
Yeah. You asked about this suprasegmental. Why is it not taken as a suprasegmental feature and as a 30-second segment? Is that the right question?
Yes, 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 yes.
Okay. Okay. So what I was telling was suprasegmental information is defined more from the speech perspective. So you do WAD on the signal, and then you take the voice segments and take a longer segment and compute features over that. In the movie scenario, you not only have speech, you have music, environmental sounds. So you cannot define a WAD over this kind of signal. If you do a WAD, you'll never. It might happen that for some movies there might not be any silence durations. So you cannot define any voice signals, because not all components of this signal are voiced signals. Some are musical signals, some are environmental signals. So rather than going for the suprasegmental definition of features, we can randomly decide on a longer segment, which is 30 seconds. In this case is a heuristic. You can go for 15 seconds or you can go for 45 seconds, it doesn't matter. But it will depend on the design of your system. Since I followed the setup of the baseline method, so that I could compare my performance with them, I used the 30-second setup. But we can always explore other size of windows and see how that performs. We can even go for overlapped windows, so that we can get even fine information extracted from the signal. Uh, but that will improve the computation load, obviously. So that is how the thing is. A longer duration, since this is a complicated task, a longer duration will give us the larger context to do the prediction. A shorter duration will give us fluctuating information, and that will be difficult to smooth. So that's the basic idea here.
That was very
But sir, I faced some challenges with regard to internet while during your presentations. I don't know if you already explained about this thing. When extracting the meaningful feature from both the audios and the visual data, does each modality require different techniques and preparation step, or is it the same thing? Does it require any different techniques for the datas, the virtual datas and the audio datas?
Yeah, the first difference is audio is basically a one-dimensional signal, whereas video image is a two-dimensional signal, and video is basically a three-dimensional signal. You have images over time. So obviously the processing of these types of signals would differ. uh, I have not explored the visual or the image modality as much as I have explored the audio modality, but the approaches that generally people use do vary, because audio is processed in a particular way. Like since we assume that the audio signals are not stationary, so we have to split them into short frames and then do convert them into a two-dimensional signal and then process it. That is how we do audio processing. In for video processing, what people do is, since for high definition videos, uh, each of the if you pause the suppose there are the video is basically a sequence of images which are very run very fast. Suppose, for example, 23 images per second. So to get a real animation, real moving or video, you need to have a very high uh, frame rate, which is the number of key frames per second. So that is a very high amount, huge amount of data to process. So what people basically do is, they, from a particular time duration, they consider, suppose 100 millisecond, they, or even smaller maybe, they extract only one representative keyframe, and that way they reduce the amount of data that they have to process. They can also subsample the images into smaller resolution, so that the data gets reduced there also, and then they do their image processing. They apply the image processing approaches on that to pass them to the models. But this is the basic understanding that I have, but I have not explored video that much, so I cannot give you much more detail about the video modality. uh, but I think there are a lot of differences. We have to go through them separately.
Okay, thank you, sir.
Thank you very much, sir. So we have already passed 20 minutes. Yeah, after that time. So I think Sarah hasn't come back yet. So I think we should conclude it here. So you have another session in I think the day after today, I guess.
Yeah, 21st.
So thank you very much. It was a very insightful session.
Thank you. Thank you
So-
for